We talk about camera matrix, and this basically is something like that, where we have a point in the three-dimensional space, and it is in the world coordinate. Then we need to do some transform into the camera coordinate and do projection. So this part of the matrix will have the rotation and the translation, capture the extrinsic information of the camera, where you put the camera according to the world coordinate. And then this K matrix basically capture the intrinsic parameters, right, of the camera. For example, like this alpha to control the aspect ratio of the horizontal versus the vertical axis of the camera. And S is a scale factor. And also, by the way, we mentioned about a homogeneous coordinate. So in 3 dimension, we just add an additional 1 here. And 2 dimensional, also we add additional 1, so it becomes like 4 dimensional, 3 dimensional. And basically, in homogeneous coordinate, this is kind of dummy. So what it represents is like this. For example, if you remember that if it have a point, let's say U, V, D, something like that. Actually, if we map it back to the Cartesian coordinate, it's like U over D and V over D, something like that. So then we talk about like, oh yes, I mentioned that like I should try to show some demo last time, but I can't find it. It turns out just was there, but I didn't see that. It's a code is in the directly below that. So it's something in MATLAB. It's a very simple demo. Just want to show you this projection. So let's say if I have some 3-dimensional data, let me just run it first. So I have some 3-dimensional data, basically have the image capture, also have the depth information for each of the pixel, or like the voxel on the image, on the object, on all the objects. So it's something like that. The original data is like this. So we have the original scene that is captured by kind of like RGB cameras, so just a normal cameras. But we also have a depth cameras that capture the depth information. You can see there's some depth information here. So then, like using projection, we can regenerate the image somehow in whatever way we like. So actually, I have another GUI, but it's a very slow one. Trying to play with some of these parameters. Let's say, for example, this is kind of the regenerate under this set of parameters. So S is for example, is the scale parameter that we mentioned earlier. Is the scale factor. So if I change a little bit, then probably the camera is kind of tilted, or like actually not exactly tilted. It's like kind of scale in a real way. And I think alpha is the aspect ratio. So if I change that they will have some effect on the aspect ratios. There's some, for example, like TXTY, TC is basically it's like where your camera is located at. So if let's say maybe I move it horizontally a little bit, then I should create an image kind of see in a little bit. It's hard to visualize. I don't know how. And also this theta XYZ is basically the rotation matrix, kind of like the parameter for rotation matrix. So anyway, just a little bit fun thing. Actually, a cooler stuff. Let's see if I should play it. Is my student just generating I'm not sure. Okay. Toes, I'm not sure they're here actually. I don't care. So no, I care. They have one valuable student on the other side, and also my student may be auditing. I don't know. Let me just play his stuff. I think he doesn't mind. So so we are going to give a presentation, and he's playing with some. So let me just go to. So okay, I'm not sure I can play the audio. I can. So he's playing with this. Is actually the Unreal Engine.
All of these objects have their own coordinate system, but you cannot see them because they are aligned at 0, 0, 0 position.
He has a lovely voice. So
now you will be able to differentiate between the two coordinate systems.
So of course, this is more more or less a.
System. All I need to know how far.
Maybe I should lower his voice a bit. So he's playing the Unreal Engine, right? So basically, like. What he was trying is trying to generate some training data. So you have a 3D object models in the whatever kind of massage that, and then you can kind of create the what you see in here. Like this is I'm sorry about that. I shouldn't touch the screen. No, I'm not sure I can play. Oh, okay. I guess I just need to let it play. I cannot forward or backward. But what I'm saying, I like to touch that part of the screen here, as you see sometimes, is showing the camera. That what you see captured from the camera. And of course, this is based on, again, the projection matrix, the camera matrix we learned earlier. Yeah, I guess I'll just stop here. So, let's go back to the slides. And so what we have talked about last time. Okay, this is the camera matrix that, assuming there's no kind of distortion or anything. So if we assume there's some nonlinear distortion, most likely this radial distortion, then you will have additional function after you do the projection. Basically, you get this x and y. You need to have an additional function to kind of take into account this radial distortion. And then we talk about something about calibration, like in the last lecture, almost finished that. So basically, like for each point, each pair of points that you know the 3D coordinates and the 2D coordinates, then you have two equations coming out. And then like our goal is basically trying to figure out this camera matrix will be all this the pointer doesn't come in. So we're trying to find all these basically all these coefficients in the camera matrix, right? So then we go all the way, and then eventually we find that it's just ended up with some linear algebra equation like this. So as we mentioned, we have some basically this camera we have some leeway here because this camera matrix is invariant, subjected to the scaling factor. So we can either set this 1 to 1, then we will have this ax equal to b, that kind of like linear system of equation here. So if we solve that, then we have x is basically the pseudo inverse of b. Basically, like in MATLAB, as we mentioned, it's basically like taking the white division of b by a on the right hand side. And then like another way to do that, like we mentioned, is like, okay, if we don't put any constraint in any of these coefficients here, I mean any particular coefficients here, but instead we can put in a constraint saying that the norm of these coefficients has to be 1. So basically, something like that. Like we say, we still try to minimize this, but as we mentioned, if we simply just try to minimize this without any constraint, then of course we will have a trivial solution that without this constraint, then we have a trivial solution that like x is just equal to 0, right? So we simply add this constraint here. Then we went through some math and linear algebra, essentially saying that basically the solution will be simply trying to perform the eigen decomposition of A transpose A to get the eigenvector of the minimum eigenvalue, and that will be the solution. And so a little bit more kind of footnote here that I like to kind of describe is that in practice, typically we won't really compute the eigen decomposition of A transpose A because it's not necessary. It's kind of stupid. Like first compute this product A transpose A. Instead, like there's something called single value decomposition. So anyone heard of that? Single value decomposition. Unix.
I think I have heard, but I can't.
You at least you heard of that, just you cannot recall that. So okay, that's normal. If you don't use that, you won't remember that. But it's something very cool and important, and you don't actually need to know a lot about that. It's actually easy to, because they have MATLAB function, Python function, all of this to compute this SVD thing, like people commonly call it SVD. The only thing you really need to know is like any matrix, like it doesn't matter to be square matrix. For eigen decomposition, it has to be square matrix, right? But for single value decomposition, SVD, any matrix have a SVD basically, and it can be rectangular. It's just saying that like it can decompose into this like U times S times V transpose, where U and V are orthogonal matrix, meaning that like each of the column, I need to make sure it's column or row. I think it's column. Each of the column are orthogonal to each other. Basically, take each of the column, you do a dot product to each other, they should get to 0, and also they are normalized. So each of the columns should have a unit norm. S is basically a diagonal matrix. And basically, you have decomposition like that, like for any matrix. And basically, you have SVD implemented like in any languages. You can find SVD in any library, basically. But if you just look at, let's say if we have like SVD for A, then we substitute that like A transpose will be B as U transpose, right? When you do A, B transpose, I need to be very careful to write because there's no erase here. So A, B transpose, remember is that you need to flip the order, so become B transpose, A transpose. So it's like that, therefore like A transpose become like B transpose, so it's B itself as transpose, S is diagonal matrix, real diagonal matrix, so or actually it's diagonal matrix, so therefore like it's still S, and U transpose is just U transpose here, right? But then like U is orthogonal matrix, so therefore like U transpose U will be just equal to identity. So this will cancel out because as I mentioned, right, each of the, if you think of U here, this is U, each of the column, let's say I can write as U1, maybe just 3 column, U1, U2, U3. And the transpose will be like U1 transpose, U2 transpose, U3 transpose, something like that, right? And when you multiply that out, you have a matrix like that, right? So the diagonal will be like U1 transpose U1, U2 transpose U2, U3 transpose U3. And I mentioned it's unit norm, right? So therefore, order of this is equal to 1. And the off-diagonal term is simply like U, for example, U1 transpose U2, something like. and all these terms will be equal to 0 because they are orthogonal to each other. So therefore, you get an identity matrix when you multiply U transpose by U. So therefore, this is gone. You just have S is diagonal matrix. S will be just S squared. S times S is S squared. So you get this. But what you see is like this exactly saying that like you can, if you see that, what you have is like this is a orthogonal matrix, right? And this is a diagonal matrix. And this is exactly the eigen decomposition of A transpose A. So this means that, I should erase everything here. This means that like the eigenvector, so therefore like V is actually simply just the eigenvectors of A transpose A, right? So therefore if we compute the SVD of A, the right hand side singular eigenvector, the singular vector will be simply the eigenvectors of A transpose A. And because the eigenvalue will be simply S squared, so again we need to pick the smallest eigenvalues, right? So it will be equivalent of picking the smallest singular values. And for that smaller singular values, we pick the corresponding y singular eigenvector, singular vector. I forgot how to recall that. That corresponding V, then V column, then will basically will be the solution. So therefore, like in practice, it's always will simply solve the SVD of A rather than solving the eigenvalue decomposition of A transpose A. And then that basically it. So after we do that SVD, and then we have we take this is like the last singular vector, and that will be typically will be the smallest one, and then we just resize that, we get back M there. And so that's basically it. So you a little bit remark again, like how many points we need again. Like we have here is 6 parameters, like rotation 3 dimensions, 3 degree of freedoms, translation 3 degree of freedoms, and then like this have 5 degree of freedoms here. Total is 11, and then like again each pair of coordinates will give you like 2 equations there. So therefore, in general, you just need 6 minimum, but we can get more, and then it will be kind of more robust. And also like finally, once you get this matrix, this whole common matrix, you can decompose it back to get K, R, and T. So we have something known as the RQ factorization. So basically, like this is a triangular matrix, and this is like a orthogonal matrix, right? So then using the RQ factorization, you get back K and R. And once you know R, then you can just get back T as well, because I assume you know K and R here. Then if you know R, then T will be just equal to, let's see, T will be just equal to, let's see, K times T is equal, oh, there's an R also here. Where's the R? Yes. Because I have this is equal to M. Then if I take K inverse on this side and then take R inverse on this side, then I will get this part will be identity. This part will give me the did I miss out something? Let's see. This if this is M, it looks like I just need to multiply by K inverse, but why I need to multiply by R inverse? Yeah, I let's see. Anyone see why I? Seems like anyone spot the? So I think like this, the whole thing, I will call it this M here. And is maybe I should just write it out carefully. I have KR and KT. If this whole thing I call it M, yeah, it doesn't make sense. So I just need to take K inverse, right? Let me go back and double check, maybe let you guys know next time. So maybe something is missing, I don't know. So anyway, so I assume the equation is right, but in any case you can get back like K, T, and R. One of the interesting part is the T, right? Because T spell where's the location of the camera, right? So therefore, like if you have the world coordinate, you capture a scene after the calibration, then ideally you should be able to, in particular if you know the K exactly, you will be able to find the location of your camera in the space. So you just take, like have many scenes here, take many photos there, and then you just can know like each time where you take the picture. So what I mentioned is some linear calibration method is easy to formulate and understand, but the problem is that it didn't take into account the radial distortion. So there's some nonlinear method that I'm not going into detail here, but actually I will instead go for demo for like open series calibration. So that actually trying to take into account the radial distortion, I mean the nonlinear distortion as well. Let's see if I have already this. I tried a couple of times and unfortunately it's quite slow. So I'm not sure like this will be. You get a tab here. So this I just kind of like get this from the tutorial open series doing calibration. So oh okay, this is very silly. Okay. Anyway, let me go back. Okay. So here is trying to do calibration now. Now they are trying to find pattern like this. So I have a grid pattern. So basically, like because you know exactly, I mean at least you know this will be on a plane, right? So that's what you assume is on a plane. And then okay, this may be hard to. I actually need to now have something like now you see they capture a couple of these. They are trying to find the grid points there. the algorithm, like already knew they are trying to see a grid pattern. So they are trying to find this grid pattern here. I just trying to be, of course you just need 6 points, right? Actually it's not less than that because each time I have much more than 6 points here. But also there's a catch here. I will miss the catch. I won't talk about the catch. The catch is gone. But anyway, it won't need that many points, but for robustness, I just take many points. I guess I try to set, I forgot, maybe 30 something points here. I hope I can get there like quickly. It just simply refuse to detect the. Oh, I'm also like, before that, like I shouldn't even, because it won't see the effect. What I want to show is I want to have some radial distortion here. So without any radial distortion, then I guess you won't see like the effect of the calibration really. Let's see if I can. I should have just that. Like where did I put it? Here. So let me do this again. So try to. So I try to add a fisheye lens here to get some kind of radial distortion, but maybe even make it even harder to capture. Let's maybe trying to avoid any reflection. No catch yet. Okay, one. Maybe I should just really move. Okay. This is crazy. I moved so close already. How about this side? I guess the dirty lens doesn't help. I got tired. I should just set like 20 or something. 45 is too much. Come on. Okay, I should move. I just like get some. It's not good actually. Ideally, you should calibrate in the sense that you have like different kind of like tilting of your calibration board, but because it's hard to capture, I just trying to cheat a little bit. So here, after it generally got the points there, just trying to get the count matrix, and so that's after the calibration, and you can see that it's more or less straight. Actually, not. It's okay. It's reasonably straight. So I guess I did. Maybe it's not too apparent like this, but if you remove the lens, it becomes very apparent the effect of the calibration. So it's or like actually, if I put this back and I should, let's say, this is without the calibration, so you can see like this is, this is more apparent. So, oops. Yeah, this is kind of more Still, probably the fish lens is not thick enough or something, but you can see the effect here. So that's about the calibration and about the camera matrix, and you guys have any questions or? So let's see. So that's one. I guess I would like to continue a little bit along this line to talk about this camera model. You see, like when you have only what we have earlier is just one camera, right? So we have one camera, and trying to maybe after calibration to get the camera matrix and so on. So that's something known as like epipolar geometry, is specifically for when you have like two camera view. So if you have two cameras put together, and then try to figure out like basically how, for example, one have a point in the 3D scene, how this point will be seen in one view versus the other view, how these two views will be correspond to each other for that point. And so this is just one example. Like you have two views here, but looks pretty similar. And potentially, if you have two views like this, it can give you some depth information. Right? If you have all these camera things are aligned well, it will be simply some triangular geometry, that kind of stuff, that we can find the depth information, and that is actually was a kind of active research area in late 90s and like early 2000s, like people taking like lots of photos or like videos of like some scene and trying to build a 3D model out of that. And this is kind of like the theoretical foundation for that. I mean, there are some more complicated geometry when you have more than two views. Like there's something known as trifocal tensor, but we won't go into that. We'll just stick with two views. So this is you can always start with just two views and then try to find the depth for that two views and then play with another two views and so on and so forth. So of course, like that may not be like as kind of like if I would say accurate than directly using 3D multiple views like geometry maybe. But let's start with the two views. And so as we mentioned, let's see, one of the most interesting applications will be trying to find the depth, right? So when you have two views, you know the disparity, then the depth is very easy to compute, right? Let's say if I have this two scene here, oh, by the way, actually I completely forgot about announcement. Like you guys have homework assignment that I put it up like for 2 weeks, actually less than 2 weeks from now. I guess it's 19 or something. That's another homework assignment. That's about stuff that I guess I already mentioned what that about like earlier. And also like for graduate students, like that's also, you need to put down what you're going to present, like, and that is like an assignment also, like it's also due on the same day. And I assume you guys all submitted the homework. There are several that still haven't. So for those who haven't, I'm talking about the video. Like if anyone is watching the video, be sure to submit it on time. Already you are not on time already, but submit it as soon as possible. Don't forget we have late penalty, like 5% per day. Yeah. So So again, like, okay, the geometry is pretty simple. This is really elementary kind of geometry stuff. So let's say if I have some 3D points like this, set up like that, and this is the OL, and OR here is the camera center, let's say, and P is the actual depth here. So we can use some simple triangular geometry. Let's say T, let's say, is the distance between the two cameras is T. Then you see like T over C, this is a similar triangle with another similar triangle like this one, right? This smaller one. And then therefore like T over C should be equal to T minus, let's see, actually this have a typo here, should be minus CL, yeah, that's actually correct. Yeah, that's actually correct. That is actually not correct. The sign is exactly flipped. I guess it's T minus XL, because XL here is a positive, right? And plus XR. Let's see. So, but I assume the equation afterwards should be correct. Just, I mean, in the sense that it should be T over C is equal to this distance over C minus F, right? So that will end up like C is simply equal to this thing here. So it will be proportional to the focal length and proportional to the distance between the cameras and inversely proportional to the disparities, I mean, between two views there. And it's kind of like you expect, right? If this thing is like, if it's like farther away, you expect it's closer. If it's like, when you see from the two views, they are kind of, well, I mean, if the disparity, okay, by the way, disparity meaning that like, when you are in one scene, you see, I guess I didn't really explain what is disparity. Disparity meaning that like at one scene maybe I sit here, and then in another scene I sit here. Let's say I supposed to sit here, but instead I shifted by this distance here, and this is known as the disparity. So we expect the disparity if larger, then it's like closer, right? I mean, it's like smaller than it's farther away. Anyway, it's like just simple equation here. But then there are several questions, right? One question is, actually the biggest question is like, how do you find correspondence of like two scenes here? So apparently, if you know like exactly one point here is equivalent to another point here, and so as like for all the other points, then we can simply compute a depth map very easily, right? With the very simple equation that we have earlier. But the problem is like, how can we find this disparity? So one thing is, of course, you can do some kind of feature kind of extraction that we'll talk about later on. Compare the feature of a point there, compare with another feature, the feature of another point there. But even that's another problem, right? We can find, let's say, each of the point in the scene, let's say we can, based on the neighborhood of that point, we can generate some feature of that point there and use this feature to compare two points. We can do that. But the problem is like we still need to find correspondence, right? So let's say for each of the points, we generate a bunch of features for all the points on the left-hand side, and on the right-hand side, we also generate a bunch of features for each of the points. Then we need to pair them up like one by one, right? So it can be really time-consuming also. You need to just, for each point on the left-hand side, you need to find all the corresponding, each of the corresponding, the corresponding point on the left-hand side for each and every of them. So this is where, when we talk about this two-wheel geometry or this epipolar geometry help, the main idea is that like if we calibrate the camera nicely, then it turns out that we'll elaborate here, that we actually don't need to search. For example, if I have point here, in general, we may need to search at the entire scene, right? I mean, entire 2D whatever scene here. But if we calibrate the scene well, it turns out that like instead of like searching the whole 2D space, you can just search along 1D line here. And we just need to search along this 1D line. And this drastically decreases the computational cost for this operation. And that's basically, we'll talk about how we have this epipolar geometry. So it's kind of like this. So we have two scenes, right? We have a point in the 3D, and this is the camera center for the two cameras on two sides, and then they are looking at this direction here for these two cameras. Okay, these two directions here. Then this point we projected to here, and this point we projected here on this scene here, this side here. So what you can see is like, of course, if everything, I mean, the setup is known as we expected here, like if the setup is known, if we know exactly where's the point here, where the point here in these 2D views here, then we know exactly where is this point in this 3D space, right? But if we only know one of the points here, I mean, I know that like on the left-hand side, I know it's here. If I don't know where is it on the right-hand side, then you see that like it can be anywhere along this line, right? And this line, as I mentioned, actually would project to this line here on this left-hand side. So that's exactly what I mentioned earlier. So assuming you see a point here, and if you have everything is calibrated, and you know this epipolar geometry things, then you don't need to search through the entire space, but you just need to search through this line to look at where's the point exactly. And this is the key idea. And now get into more math. So please be prepared. I will try to be, but this is actually pretty nice math. So it's not hard to understand also. And please stop me like if you have any question, because I think like all of you guys can understand, and stuff like that I believe is much easier to learn like full lecture rather than you learn it yourself. Like if you try to grind through a book, like for stuff like that, it will take you lots of time. But if you just try to understand what's going on, like through like online lectures or like anywhere, like listen to how people talk about this stuff, it's much easier to understand. So basically the setup is as we mentioned. I just give some terminology here. So this line connecting these two camera centers, we call it the baseline. And then like the baseline is intersecting of these two views here, right? And the intersecting points are known as the epipoles. It's basically like the point intersect with these two image planes here. And this plane here that I draw here in gray is known as the epipolar plane. And then like the two lines here is known as the epipolar lines. So using this terminology, so what we mentioned earlier is like if we have a point here, see on the left side view, so we just need to look at the epipolar lines, corresponding epipolar lines on the right hand view to find the correspondence. So this is just some example of like when you have like different setup of the different camera setups. And let's say if we have set up like this, then we have, in this case, we cannot see the epipole. The epipole will be like this. All this is drawing the epipolar lines here. So you see the corresponding this point correspond to this point here. And this point, if I don't know what is the correspondence on this other side, it would be like on this epipolar line here. And so on, like we have draw all the epipolar lines. And all the epipolar lines are supposed to converge to the epipole. And here, like because the image plane, basically the camera is not big enough, the epipole is actually far away, like you cannot see it. And if you have parallel scene, the epipole will even like at infinity, basically. Because remember the epipole is basically the two camera center, kind of like when you have the baseline will be connecting to two camera center. Right? The epipole is basically the intersection of the baseline with the image plane. So what we have here is basically two cameras is looking straight ahead, like in parallel. So there's no way the two camera center can intersect with the the baseline that connecting to camera center can intersect with the image plane. So therefore, the epipole will simply converge at infinity. In other words, this all epipolar line, epipolar lines will be parallel. And that's another example that actually you have like two camera is actually one ahead of the other. So in this sense, the epipole is actually right in front, kind of. So because you connect the baseline again, or connecting the two camera center to get the baseline again, then the baseline basically just cross the image plane in the basically near middle of the image. Really need some water. And wow, this is crazy. Okay, so more epipolar line and so on. Let's get down to some math. So we have something. First, we start with something known as essential matrix. And this is the interesting stuff. If you guys also in my other class, if you know who, I must have mentioned Jeffrey Hinton. If you still remember who is Jeffrey Hinton, this is invented by his advisor, and his advisor is a cognitive scientist. He invented that like in early 80s or early 80s, late 70s, something like that. And so the essential matrix is trying to describe the following. So again, we have the same setup as before. Now let's say we have the point we're interested to look at, again call it X. Now be very careful, like the notation is maybe a little bit, it's not difficult, but just a little bit can be, need to be careful. So basically I have two camera view, and one is shooting in this direction, right? You can think of like this is the Z direction of this camera view, and this is the Z direction, this is camera view, and so on. So they are two different camera views, right? So therefore, like for the same point here, let's say this is the 3D coordinates of under these two different views, and I call it x hat L and x hat R. So I have two different coordinates. They are Cartesian coordinates, not the homogeneous one, just the normal Cartesian coordinates. But they are different, even they are pointing the same view here, because just I'm looking from two different cameras, like using two different cameras coordinates. Now, what the essential matrix, the end result is like under this two different set of coordinates that capturing the same view, I can find a matrix E called essential matrix will satisfy this, and this satisfies for every point in every 3D points in the scene. And that E actually turns out to be very simple. Let's call T is the translation from the left-hand side to the right-hand side. In other words, like this T is basically just like what's the location of the right-hand side camera center in terms of the left-hand side camera view. And then in that case, okay, I guess I can bypass this. We have this earlier last time. In that case, also let's call R is basically the rotation from this camera view to this camera view. So if you want to, let's say, so in other sense here, the rotation will be more or less in this direction, right? You expect this will be the rotation. So if I want to translate, therefore I translate this coordinate to this coordinate, will be simply first translate this to here. So originally the coordinate this. Now I subtract this here, it becomes something like this, and so therefore become this. Now, but this is according to these coordinates, right? Coordinates I have the CS is pointing this direction, right? So therefore I need to rotate back. So I have another additional rotation just to rotate the C coordinate back to here. So therefore, like I can simply connect this coordinate on the left-hand side to right-hand side by this simple equation here. So no question. It's pretty simple, right? Now with this thing, let's digress a little bit. Let's review a little bit what cross product have. Cross product mean. I hope you guys still remember what cross product. So when you have two vectors in 3 dimensions, the cross products will be like you have a kind of rectangle or something, will equal to a vector that is kind of perpendicular to the plane of the that spanned by the original 2 vectors. And I think you probably came across it that in EM or something, electromagnetic, you have that. And the cross product will be computed like this, right? If you can still remember. And there's also like some property of cross product is like they turn out the magnitude of that cross product will be just the magnitude of U times magnitude of V times sine the degree between the 2 vectors. Let's call it theta. So therefore, if these 2 vectors are parallel, then the cross product will be simply equal to 0. And also, as I mentioned, the cross product can be represented like this. So this I guess you are familiar with, or like you should came across before in EM, so on, but you may not have think of that this way. So I write like this, but I also can write it in matrix form. So in the sense that like you can think of like U cross V as some kind of operation applying to the V vector. So such that you can think of, oh, now you have a kind of a U cross operation matrix multiplied by V. So you can easily figure, I mean, like this is just simple algebra, but it turns out just like this. And also like one interesting fact is that if you look at this matrix, the rank is actually just less than equal to 2. You simply can compute the determinant of this guy, right? And you will find this is equal to 0. Therefore, rank will be less than equal to 2. It cannot be full rank. And now go back to what we have earlier. So I will claim that the essential matrix is simply given by this. So will be just the cross product matrix that I introduced earlier, and I have earlier here is Ux, right? I mean U cross something. Now I have basically T cross something, that matrix operator. And after the matrix operator, I apply a R matrix kind of rotation operation, and this will be my E matrix. And that's it. That is my E. And now I just need to prove that, right? I need to verify that. So let's say let's look at what is this. I hope that this is equal to 0. So let's just substitute that into this one. Now look at this what I have here. I didn't do anything. This part I just substitute this into here, right? So I have this one. Then now R, because it's a rotation matrix, is orthogonal. So R transpose R is just 0, so it's gone. And now this T cross X hat, I can just write it like this, right? This is just a T cross operator is equal to that. And this multiplied by this vector here. This whole thing is actually a vector. Right? This is just a vector. Right? It's just a dot product, right? So I can write a dot product form here. So no question. So now, but then like because t cross p has to be perpendicular to the plane spanned by t and xr, right? So therefore, like this must be also perpendicular to like t xr minus t. So you know the dot product of like two perpendicular things will be simply equal to 0, right? So therefore, like it be just equal to 0. And actually, and as I mentioned, like because like t cross operator has rank less than equal to 2, right? And when you have kind of the rank of a product, it cannot be have rank like bigger than each of the individual inside the product, right? So therefore, like the rank of E, since E is equal to R times Tx, has to be less than the rank of Tx has to be less than 2. So we already know like E cannot be full rank; it can only be has rank less than 2. Now let's try to wait a sec. Okay, let's try to look at what happens if I try to multiply E by any points lie on the baseline. So let's say if I have a point that lie on this baseline here, again the baseline connecting the two camera center. Let's say again like XR0 is the point according to the coordinate on the left hand side here. Now let's look at the product here, like RTX XR0, and this will get me this way because this is just a cross product operation, and this will be equal to 0 because I just look at this guy here. T and XR lot is parallel, right? T is pointing to this direction, that is T is here, your center is here. XR lot is also like is here, the center is here. It's two parallel lines, so it's just equal to 0 T cross XR lot. And then similarly, we can also know that like if I have E transpose, I have E transpose and try to multiply by XL lot. XL lot is basically the coordinate according to the right hand side point of view. So basically according to the coordinate on this side. And then again substitute this one E is equal to RTX. Then transpose of that I just is TX transpose this guy. And then this again, this will be equal to identity, right? Because R is just orthogonal. Then TX transpose. Remember, T is an anti-symmetric matrix that we have. If you look at this here, this TX, this cross-product operation matrix is like this, right? If you do the transpose, you will just get a minus of that, minus that matrix. So this will go to here, this to go to here, this go to here. So it's just the sign will all flip. So therefore, like transpose of this guy is just equal to minus this one. So then again, let's see. This is just equal to T cross this guy, right? Again, this will be equal to 0 because x0 minus T is like that. X0 is here like that, but it's still like the direction is still like parallel to this line here, right? So it's still parallel to T, so therefore again it's equal to 0, the cross product. Now that's the essential matrix. Then there's something known as the fundamental matrix. Is an extension for that. So what it is simply, now let's consider we have the 3D points here. Now project back to the image plane. So I have like this is again like XR hat, and XL hat is basically from two different camera point of view. And then let's say small XR here is like the projection to the left hand side, and then small XL is the projection on the right hand side. Oh, okay. Did I say left or right? Sometimes. Okay. That's infectious disease. My wife cannot like distinguish left and right, and apparently I just got this disease also. Like it's white. Anyway. So anyway. Anyway, so if we do that, then we introduce this XR and XL. We have a so-called fundamental matrix. Have something similar to the essential matrix. It's also like the product will be equal to 0. Oh, okay. By the way, I need to be careful. This XR is the Cartesian coordinate. XL, big X here are all the Cartesian coordinates, but the small x is the homogeneous coordinate. So that means that, okay, let me just check anyone is still awake. So what's the dimension of XL and small XL and small XL? What's the dimension of big XL and big XL? It's a vector, but how is a 2 dimension, 3 dimension, 4 dimensions? Yes. How about the small one? It will be 3 also. Remember that whenever we talk about homogeneous coordinate, we need to add 1 more dimension to that, 1 dummy dimension. So yes, it after projection is shrink to 2 on the image plane is 2D, but then because we are now looking at the homogeneous coordinate, we'll have 1 more dummy dimension. So actually, both F and E is 3 by 3 also. F is also a 3 by 3 matrix. Now, it's not recalled from last time. We recalled from earlier that we have the common matrix like this way. So, and then now if we assume everything is aligned, that's exactly what's going on here. We have the coordinate that we are playing with on the right hand side and left hand side exactly aligned with the world coordinate. So our world coordinate, or like the coordinate that we are using to describe this XR and XL, is exactly aligning for the white camera. Is exactly aligned with the white camera coordinate, and also for the left camera is also exactly aligned with the left camera coordinates. So therefore, like for both R and T in this case are just trivial. So R will be just an identity matrix, and T will be no translation is just equal to 0. So then in that case, your projection will be purely just depend on this K here. So what you have is like this projection is just equal to, it will just reduce to like X is equal to KX. So and note that also like is actually, if I want to, in this one, actually if I go more detail here, it will be like X is equal to K 0 X1, something like that. X, Y, C, and this, I call it big X here. This thing will become something like that. And this will be simply equal to KX. I'm sorry, let me just use an eraser as a something like that. What I mean is like, this is the Cartesian coordinate, right? And this whole thing is the homogeneous coordinate here. And after the multiple is simply equal to k times x. X is the Cartesian coordinate now. So this is 3 by 1. This is also 3 by 1. And this is 3 by 3. So everything looks right. Now then, that means that the relationship of this and this one is simply equal to k times this guy, right? And similarly, this guy is simply like k times this guy, right? Then I just put them together, right? So then F is actually very simple, as long as we understand the essential matrix. If I pick F is equal to this guy here, then I just have now XL, I know is, or for example, XL is k times big X. XL is like k times big XL. So F transpose, I just flip the order. So in either case, this part and this part will be cancelled. So therefore, I just get back this. And earlier, we know that this product is just equal to 0. This is the property of essential matrix. And therefore, we have the fundamental matrix is just equal to this. And by the way, also like if we have epipole, or like any line, any point along the baselines, as we mentioned earlier, that one, if we multiply by the essential matrix, is equal to 0, right? Now, if I project this one to some point on this plane, again, I multiply by the fundamental matrix, it turns out it will also be equal to 0 as well. It's very easy to show as follows. So I have F is equal to this guy here. Then, again, like this point here, yes, this point here, that basically the projection of this 3D point here is just equal to this guy here. And this one, as we know, is a property of essential matrix, is just equal to 0. And similarly, we have something similar that if we have a point here on the baseline that projected to the, basically, or like I should just say that this is basically the epipole. Right? The epipole on the left-hand view multiplied by F transpose will be just equal to 0. And also the epipole on the right-hand view multiplied by the fundamental matrix also equal to 0. So it's interesting because I was, it's interesting because let's consider one more thing that again, like if you look at homogeneous coordinates, something is very nice. If you think of in homogeneous coordinate, this is a point, right? Now, this is like the typical line equation in 2D, right? This is a line equation, as you know. And if you look at any point on this line, I should have ABC times XY times 1 equal to 0, right? Is that? I mean, this equation, I can write it as ABC at the row vector multiplied by, again, this is so hard to write. Erase this again. X, Y, and 1, right? This is equal to 0. This is exactly equal to this one, right? And this, I can call this L. And this equation is just saying that L transpose, let's say L is a column vector. L transpose, I call this P here. P is equal to 0. So I can use, again, like a kind of like a 3D vector to represent a line. So basically just a 3 numbers to represent one line like this. And also, I have an interesting property that like simply like P dot L, the inner product, or like P transpose L is equal to 0 if and only if the point P here in the homogeneous coordinate is equal to is on the line. So now, why I kind of digress like this? Because if you think of that, like this is a point in homogeneous coordinate, right? So therefore, I can think of this is something describing a line. So I have this equation is basically saying that this as a line actually is a line that passing through this point here. So then also remember that like we already mentioned, like f times epipole is equal to 0, that we have like 2 slides before. Then we arrange the term again, like I can have E transpose times this. Again, now we think of this as a line. It's also equal to 0 because, okay, I just rearrange the term. Then this I have F transpose E appear that I know earlier is 0. So I have this is equal to 0. So that interesting thing is saying that, okay, F transpose F times X here, if I see this as a line, pass through not just XL transpose, but also the E transpose. So that means that, okay, let me draw where is it. That's actually this line, right? It passes through both this epipole here and here. It means that like if I know the fundamental matrix F, and I multiply by this XR here, that get me the line, and that line is exactly the epipolar line. And that's what we want at the beginning, right? So if we have everything known, like we know the fundamental matrix, actually we don't need to know everything, but as long as we know the fundamental matrix, and now if we know a point, we have a point of interest, and then like we multiply that by F, that get us the line, and that line will pass through the point that we are interested in the other scene, in the other view. I guess I see like some of you guys are packing, so I guess I will stop here. So we'll kind of like come back next time.